Data centers are hitting a physical wall. Power demands are pushing server racks to their absolute thermal and operational limits. The International Energy Agency projects that data center electricity consumption will roughly double by 2030, driven almost entirely by AI workloads. We are reaching the point where the International Ethernet Consortium is redesigning Ethernet itself just to handle the raw throughput required by high-performance computing. Even as Ethernet is re-optimized for AI scale, the logic governing the data remains reactive. These architectures monitor congestion and packet loss, but they only trigger a response once those bottlenecks have physically formed. Waiting for dropped packets or reactive alerts to trigger a response means the damage is already done. By the time corrective action begins, tail latency has degraded and compute cycles are wasted. Standard observability tools monitor link utilization and queue depths against simple, static thresholds. If a queue hits 90%, an alert fires. High-speed microbursts surge through fiber optic cables in microseconds, entirely evading these static monitors until the packet collisions occur and buffer pressure becomes overwhelming. Resolving this requires a control plane that actively predicts congestion states before the queue depth spikes. This does not mean replacing foundational protocols like TCP/IP, Ethernet, or segment routing. Instead, it requires layering a mathematical control system directly above existing network hardware, utilizing the telemetry these protocols already generate. By introducing this intelligence over the existing infrastructure, a data center stops reactively tracking alerts and begins predictively modeling its own behavior. This diagram outlines predictive geometric networking, PTCP memory, TNQG geometry, and safe agency. PTCP ingests telemetry, creating infrastructure memory. TNQG translates that into geometric emergent distances. Finally, a champion-challenger layer bounds actions, shifting the model from reactive packet movement to predictive geometry. The process starts by ingesting raw data streams. Using standards like OpenTelemetry, the system pulls in trace logs, GPU saturation metrics, and storage pressure states. Treating these as isolated data points leads to alert fatigue. Instead, the system models the network's overall behavioral pattern of life across all available dimensions simultaneously. It achieves this using a mathematical process called kernel density estimation, or KDE. KDE transforms thousands of noisy, discrete telemetry samples into a smooth, continuous probability field. This field defines exactly what normal operational behavior looks like, shifting dynamically as the network state changes. The infrastructure now possesses a dynamic, predictive memory of its own baseline, rather than relying on a static historical log of past failures. Modeling a multi-dimensional state tensor for an entire AI factory requires processing an exponential volume of data. Attempting to do this in real time is computationally impossible. To bypass this limit, the PTCP layer uses tensor-train compression. This algorithm collapses the massive behavioral state down into a minimalist chain of compressed data cores. These lightweight cores sit directly near the data path, enabling microsecond queries at the switches without waiting for a central server. This specific compression technique bridges the gap between exponential data spaces and realistic hardware deployment constraints. This flowchart illustrates the control plane deployment. On the right-hand column, TNQG geometry extraction occurs within the data flow. The system calculates a localized anomaly score directly from the tensor-train cores, feeding that score straight into the policy envelope. At the TNQG layer, a high anomaly score is interpreted as a physical topological defect in the fabric. This calculates an emergent distance. High-capacity paths shrink, drawing nodes closer, while anomalous paths are mathematically stretched. Orchestration layers apply this geometry to route traffic or allocate memory along predicted geodesics. These are the mathematical paths of least future resistance. By operating on emergent geometry, the network routes around high pressure zones and bottlenecks before conventional monitors even register a drop in performance. Unconstrained autonomous control introduces severe risk. Handing full routing authority to a new AI model could induce destructive network oscillation or cause cascading outages. This graphic shows an 8-phase deployment method prioritizing trust before granting network action. In steps 1 and 2, the system runs in shadow mode, passively ingesting telemetry to learn the network's pattern of life. During step 3, the system must prove its predictive lead time by forecasting congestion events before they occur. In step 4, it enters advisory mode, generating routing and memory recommendations solely for human approval. No production traffic is touched until the mathematical models demonstrate complete accuracy and measurable lead time in a live, read-only environment. Once operational trust is proven, the system moves to phase 5, activating autonomous control safely. It achieves this through a champion-challenger model. The challenger model is quarantined to learn, while the champion operates in production, strictly constrained by a hard policy envelope. If the champion attempts a change outside those boundaries, the action is immediately blocked. This bounding mechanism guarantees zero policy violations and prevents uncontrolled oscillation while maintaining automated response speeds. In the final phase, this safe agency scales out across the entire digital fabric, unifying control across compute, network, memory, and security domains. This software-defined control layer multiplies useful GPU utilization and aggressively lowers tail latency, extracting significantly more value from existing data centers without massive hardware refreshes. Infrastructure gains a measurable operational advantage when it possesses the memory to predict its behavior, the geometry to map its paths, and the bounded agency to act safely.